This was Larry some time ago, and this is him now. Larry thought it was a good idea to make a 3D engine. Though Larry didn't expect he'd have to learn linear algebra. And this is me. I am Larry.
Mining away. I don't know what to mine, I'll mine this anyway. In this Minecraft day, so beautiful, further down. What's that I found? Mine diamonds. Mine diamonds.
Hello. So how do we begin? Maybe philosophically? So, what's a 3D engine anyway? It would be good if we knew what we were building. Oh, so a 3D engine makes a 3D scene from simple commands. Who will have guessed that? Now let's explain it in more detail on a simple example. Now, what can we see in this absolute gem of a game, apart from the astonishing graphics? We can see the simplest form of a 3D render. That's exactly what we need. We can describe the scene like this. We have some point C, as in camera, very original, I know, and some point A, which is a vertex of a cube, a torus, or some absurdly complicated shape. Now, how can we see this point? Well, we can send our rays from our camera into the scene, or more accurately, until the render distance says otherwise. And how do we do that? Now, let me introduce you to our long-lasting friend on this adventure, the unit sphere. He's basically the twin brother of the unit circle, and he'll help us understand what's going on with these sines and cosines in here. Using this unit circle, we'll navigate our array, which was sent under some angle from the ground and some angle to the north. Using the angle given by the camera on this particular ray, we'll calculate its one step in x, y, and z, like this. So in a simple 2D circle, we will take the formula from one angle like this. But in a 3D sphere, we'll have to take into account the angle from the ground up, and as the angle up into the z-plane increases, we notice that the step in 2D decreases, so we'll multiply x and y by the cosine of the angle from the ground. Now using this formula we'll send our ray to go and jump across the vast plane of our game. Now how will this be useful? We will let it jump in a for loop, using the render distance as a border, and in every iteration we'll ask it the same question over and over again. Have you collided with an object yet? If his answer is no, then let him continue on his journey. Otherwise, let the pixel on the screen from which this ray came from be colored in the object's color. You may ask how we'll know if the ray has collided or not, and the answer is simple: AABB collisions. Basically, we'll manually check every axis of the object and ask our ray, using its current position, if it is inside. And that's it, using a simple for loop for sending the ray in an arranged order, we'll get the picture. Now, after some coding, we can turn this concept into reality. And now we can see how it looks. Yeah, it's not good. So this was Raymarching. But fortunately for us, there is a way to turn this concept into a much faster 3D engine. And it's not even that different from what we're currently using. So let's first describe the issues of Raymarching before making a better alternative. Our for loop checking every one jump misses a block which is 0.5 units long, and if our array goes through a corner, We don't even have to detect that. Now, how do we solve this? Now, let's first rewrite our concept using arithmetics. If we say our origin point from where our ray came from is named O, and if we add a unit vector v to our point O, we'll get here. And how far is that from our original point? That's exactly 1 unit of length far. Now, in Raymarching, we've been repeating this addition of the unit vector v multiple times, so we call it t. We can now write this into an equation just like this. Now, what we've been doing in Raymarching is that we've only been using t's which are integers. Now, what if we make the t also a decimal? How will we detect the collision now? We'll simplify our cubes to their inner spheres and use the radius r to know if our ray hit the sphere. And that will be known if the closest point of our ray is closer to the center of the sphere than r, the radius. We can see that we have a right angle triangle here. We want to know this variable right here and this variable right here. This variable right here will be our t, and we'll use this variable to compare it to the sphere's radius. And we can easily calculate the absolute distance between the point O and S using Pythagorean theorem. We also know the values of vectors coming from point O, and using values of those vectors we can calculate the angle right here. But to do that we'll need to introduce a new mathematical function. We have these two vectors and an angle between them. We know where the vectors are pointing and we want to know what is the angle between them. Let's first imagine that it's a sunny day and the light is creating a shadow from vector 1 onto vector 2. The length of this shadow is equal to cosine of the angle between them times the length of vector 1. This alone doesn't help us, but let's construct a rectangle with sides of this shadow and the vector on which the shadow is being cast. We'll calculate the area of this rectangle like this. And now comes the trick. The area of this rectangle is also equal to the area of these two rectangles combined, made from the values of the vectors in individual axes. So the full equation looks like this and gives us a way to calculate the angle from the vectors themselves. So let's get back to our original problem here. We're looking for d, the value which we'll be comparing to the radius of the sphere, and t, the distance from the origin point to the point where our ray has collided with the sphere. We can draw the two vectors coming out of point O, with v1 being a unit vector, so it has an absolute length of 1. That we know from goniometry that t is equal to the cosine of alpha times the absolute length of vector 2, which also happens to be the exact same equation as dot product of vector 1 and vector 2. So we calculate t as the dot product of vector 1 and vector 2, and then we simply calculate d from the Pythagorean theorem. And after some coding in C++, where I basically used a for each loop for every cube of the cube list, and in this for loop we basically check if the distance t is smaller than the last distance t that we used, and if it is, then we'll rewrite current color to the object's color, and here's the result. It's much faster than my other attempt in Raymarching, but it's still painfully slow. To solve this issue, we shall again address the problems of raycasting. We're sending a lot of rays, which is pointless because many of them just go outwards into space and don't hit anything. Instead, we should try to project important points like vertices from an object onto our screen, instead of projecting every single pixel that we see. and then we just should connect those points instead. How shall we do that? Well, let's bring back our model with point O being the point in which our camera is located and point A being one of those vertices. Now, first of all, point A is described by some global position, but that's not what we want. We want some local position because our camera is pointing somewhere. We shall call this direction its heading vector. We shall create also two other vectors which are perpendicular to the heading vector, and they shall be called y of camera and x of camera. Because what we are basically going to do with them is that we are going to transform the point's position to a local position from the perspective of the camera. So when the point is going to be further in the direction of the heading vector, it's going to have a bigger z from the perspective of the camera, and when it's going to be more right from the perspective of the camera, it's going to have a bigger x, and so on. Let's take a closer look at the scene here. We are going to draw another vector, AO, which will not be a unit vector this time, and it will be pointing from point O to point A. Now, based on this vector, we'll make one of the most beautiful set of equations, I think, which will be just the dot products of each of camera's heading vectors and this AO vector. Because the camera's local vectors are all unit vectors, we will just get the point's transformed position. So the new z of this point shall be the result of the dot product of vectors AO and z of camera. Great, now we have successfully transformed the point to the camera's perspective. But that's not all. We must also now project this point onto our flat screen, and we shall do that with a thought experiment. Imagine that you have on your screen a glass of water, which is pretty close to you. The two edges of the glass seem about, let's say, 5 units of length away from each other. Then you open the window and you see a hill, which is from your perspective also 5 units of length wide. But you also know that in reality, the hill is much wider than the glass. So when we express it in mathematical terms, we shall divide the position of the point by its depth from the camera, and also we shall multiply it by some focus. Now, what is this focus? In games, when you're choosing FOV, what you're basically choosing is the angle which the camera holds with the edges of the screen. And from this angle, we want to calculate the distance of the camera point from the screen, which we do like this. Now, if our screen were to be a square, the f of x and f of y would equal, but most of our screens are rectangles, so we also multiply f of x by the aspect ratio, and after some bit of more coding, we can get the result. Now this is much better because it's much faster, and the only issue that we now face is how to fill in those sides of these squares. And how to do that? Now, first of all, we shall divide our cube into triangles, just like this. This allows us to take a closer look at each triangle individually. We shall find the highest and lowest point of our triangle, and then start to draw stripes from the top to the bottom, decreasing the y of the current step by 1 every row. But how do we know where the rows start and where do they end? We will resolve this issue by calling the start of the row P1 and the end of the row P2. Everything with bigger x than P1 and smaller x than P2 is in the triangle. But what values of x do those points have? We can calculate this based on their proximity to certain points. We know that the sides of the triangle are linear, so the x of the point P1 will be the x of the point A1 plus the difference in y between P1 and A multiplied by some constant C1. Similarly, P2's x will have the same equation, just with a different constant. However, how to calculate this constant? Due to the point C lying on the same line as P1 and A, we know that it as well has to follow this equation. And due to the fact that we know C's position, we can just flip this equation and calculate C1. Similarly, we'll calculate C2 using this same method, just with point B instead of C. Now we can fill all the stripes in. Oh no, our rule broke when we hit point C. That's because we are still trying to follow the same line as we've been on, but the triangle drifts to a different line in this point, so we have to add a detection for when our y is lower than C's, and when it is, use a different constant, C3, and we'll get C3 using a similar trick, just with B and C now. Great! Now we've colored in a cube. But what if we want to draw another cube in front of it? How will we know which pixels belong to which cube? We'll do this by having two lists containing information about every pixel. The Z list, which contains the depth from the camera of every pixel, and the RGB list, which contains color of every pixel. And when we want to draw a new pixel on some place, we'll first check if it's closer to the camera than the pixel in the Z list on that position, and if it is, we'll update the color list and the Z list to the current pixel's information. But how do we know the Z of every pixel? Well, let's get back to our triangle here. We know the positions of every vertice and even their Z's. How to transfer that to the point? It's pretty simple. We'll use the same old trick we've used before to determine P1's x. We'll assume that Z changes linearly in this triangle. So we'll construct this equation now with two constants and the difference between our point and the point A. We'll get C1 and C2 from these two equations. Due to the fact that we know the positions of these points, we can calculate the difference between them. So we get our constants. But oh no, we made a mistake. We incorrectly assumed that Z changes linearly in this flat triangle, which it does not. But fortunately for us, the inverted values of Z does. So when we change the Z's of the vertices to their inverted values, we'll get the correct constants. And then we'll get the correct inverted value of Z for that point. We can then invert it again and get the Z of that point. And after a lot more coding and optimizing, we can finally get a 3D engine which doesn't lag and is actually usable. This is great. It can display even 100 cubes and it doesn't lag like the other ones. Of course, I didn't talk about everything I did in this engine in this video. For example, like these rotations and transformations or lighting, which I'll probably explain in the next video. I hope you like this video and I'll see you in the next one.